Imagine you're standing in a vast orchard filled with orange trees. The sun is shining and ripe oranges hang from every branch, stretching as far as the eye can see. You decide to pick some and take them home. As you start collecting, one by one, you begin to count. 1, 2, 3. The numbers flow easily at first, each orange adding to your basket. But soon, you realize that no matter how many you pick, there are far more left untouched. You pause and wonder, what does it actually mean to count? Can everything be counted, or are there quantities that transcend our ability to tally them? Counting seems simple, something we learn as children, but beneath this everyday activity lies a world of mathematics and philosophy that touches upon the fabric of space-time, the depths of your mind, and the infinite. Back to the orchard. You've picked up hundreds, maybe thousands of ripe, juicy oranges. Counting each one individually is tedious, but easy enough. But what happens if you want to count all the oranges that could ever grow in this orchard over an infinite time? Suddenly, the simple concept of counting takes on a whole new dimension. We step into a realm where numbers stretch beyond the finite. Are some quantities so immense that no matter how hard we try, we simply can't count them all? To unravel this mystery, we'll start by diving deeper into the fascinating world of numbers and functions, which will lead us to explore the very nature of uncountability, space-time, and your mind. If you're curious about some of the more technical details behind these, then check out the white paper link below. To begin, let's consider two key types of numbers, natural numbers and real numbers. Natural numbers are numbers we use to count discrete objects, 1, 2, 3. They're the building blocks of mathematics and the first numbers we learn as children. Picking oranges one by one and counting them uses the natural numbers. Real numbers include all the whole numbers, rational numbers, which include any fractions, and irrational numbers, which include numbers like pi and Euler's number, e. Essentially, the real numbers represent any point along the number line. Between any two real numbers, no matter how close, there are infinitely many others. Measuring the exact distance between two oranges down to infinitely many decimals involves using the real numbers. But numbers alone aren't the whole story. To understand countability and uncountability, we need to see how sets of numbers relate to one another. This is where functions come into play. A function relates each input to a specific output. For instance, I can have a function that takes your orange and doubles them. When comparing different sets of numbers, especially infinite ones, three types of functions are essential. The first one is one-to-one or injective. Here, every input leads to a unique output, but it doesn't have to cover the entire set. Next, we have onto or surjective. Here, every output is mapped to an input, but the mapping doesn't have to be unique. For example, two elements in A can map to the exact same element in B. Lastly, we combine these two mappings for a function that's one-to-one and onto or bijective. Here we have a perfect pairing between inputs and outputs. Every mapping is unique and covers the entire sets. Establishing a bijection between two sets shows that they have the same number of elements or equal cardinality. For example, imagine you have 3 dogs and 3 cats. If you can pair each dog with a unique cat, one-to-one, and every cat is paired with a dog, onto, then there is a bijection. So the set of dogs and cats have the same number of elements or equal cardinality. Even infinite sets can be compared using these functions, which is why they're so dang useful. With numbers and functions down, we now have the tools to explore what it truly means to count. On one hand, a set is countable if elements can simply be listed. More rigorously, this means a set can be put into a bijective correspondence, or one-to-one and onto, with the natural numbers. For instance, a set of 10 oranges are countable because I can list them. Looking deeper, the set of natural numbers is countably infinite because you can also list this one by one forever. This means that countability and infinity are not mutually exclusive. You can have an infinite set that is countable. On the other hand, a set is uncountable if its elements are too large to list. The real numbers between 0 and 1 are an example of this. Between any two real numbers, there are infinitely many others. More rigorously, no matter how hard you try, you cannot create a bijection between the real numbers and the natural numbers. To better understand uncountability, let's join Joe and Misty on an adventure. The two best friends have a special ruler called Deep Rule that promises to measure and count every single possible measurement along a 1 meter stick. When using it, Deep Rule displays an infinite list of measurements and claims,
"Boop boop beep boop, I have counted all possible measurements between 0 and 1 meter. Boop boop."
Misty, being the smart cookie she is, challenges this claim. She constructs a new measurement differing in at least one decimal place from every number on Deep Rule's list. Specifically, Misty's first digit differs from the first digit of the first decimal point of the first number. So instead of 2, she picks 3. Her second digit is different from the second digit of the second number. Instead of 2, she picks 3 again. Her third digit is different from the third digit of the third number. Instead of 3, she picks 2 this time, so on and so forth. As a result, her measurement isn't on the list because it differs from every single number listed by at least one decimal place. Unable to fathom what just happened, Deep Rule outputs
Processing cannot compute.
and bursts into flames. This is Cantor's diagonal argument. It proves that no matter how hard you try, you can't match every real number between 0 and 1 with a natural number. In other words, there is no bijection between the natural numbers and the real number, which means the real numbers don't meet the definition of countable. Instead, the real numbers are uncountable, a larger infinity or a larger cardinality than that of the natural numbers. Succinctly, the argument comes down to, for every number that you list, even an infinite amount, I can always list a number that you didn't. But why does uncountability matter in the first place? Because space and time are both based on the real numbers, they are uncountably infinite. Between any 2 points in space or moments in time, there are infinitely many others. This reflects the concepts of impermanence, or everything being in a constant state of flux, with new points in space and new moments in time always emerging. This uncountable nature has profound implications in physics, especially general relativity. It reveals a universe richer and more complex than any direct measurement can capture. And it may even connect to phenomena like dark energy, which is thought to drive the constant expansion of space. If you're curious to learn more, consider subscribing so you won't miss out our upcoming video on dark energy later this year. Now, consider your own mind. Just as space and time are uncountably infinite, so too is your idea space, the hidden realm of your thoughts, emotions, sensations, and perceptions, which is always changing. To test this, simply sit for 20 seconds and observe your thoughts. Can you count them all? No. For every thought you notice, new thoughts arise. The landscape of your mind, of your personal idea space, is uncountably infinite. It's always changing, never the same twice. The same holds true for macro idea spaces, the interconnected consciousness of a multitude of individuals. For instance, before Isaac Newton formulated the concept of gravity in 1687, the idea of gravity wasn't part of anyone's idea space. Where was it on the infinite list of ideas before? Nowhere. It was an unknown unknown. It didn't exist. Then, when the new idea emerged, it was outed to the uncountable expanse of human knowledge. The same holds true for the idea space now. Where was that idea in the infinite list before? As John Wheeler, the man who coined the black hole, said, "We live on an island of knowledge surrounded by a sea of ignorance. As the island of knowledge grows, so does the shore of our ignorance." So, what does it mean to count? Simply put, to count means there is a one-to-one and onto mapping, or bijection, between the natural numbers 1, 2, 3, and whatever it is you want to count. But counting is more than just tallying objects. It's a gateway into understanding different sizes of infinity, the uncountable nature of space-time, and the vast, immeasurable landscape of your own mind. Recognizing the uncountable helps us appreciate the impermanence of the universe and the limitless potential within ourselves. If you're curious about how your mind relates to the universe at large, then consider checking out the Idea Space book, linked below. Overall, if your idea space or your mind is uncountable, it means you have the capacity to learn a profound depths of knowledge. As Naval Ravikant, founder of AngelList, once said, "The means of learning are abundant. It's the desire to learn that's scarce." If you enjoyed this journey, consider liking this video and hitting the notification bell so you won't miss out the next video. In the next ones, we'll talk about macro idea spaces, topological singularities, Clopin, and a lot of other fun stuff. So we shall see you then. Adios, choo choo, bye bye, peace.